Good evening to everyone. Welcome to the sixth problem solving session for the course on concrete technology. I am Sedu Nayagam, a PhD scholar in the Civil Engineering Department at IIT Madras. So we'll start the session by looking at an overview of the concepts that were taught in the lectures for week 6. So week 6 had 3 lectures, and this week we continued with the mixed design. So in the previous week we looked at two different methods. One is the IS method, the other one was the British DOE method. And in this week we looked at the ACI 211 method for concrete mixed design. And we also looked at a design example using the ACI 211 method. So that was in lecture 17. Then in lecture 18 we looked at the packing density and rheology in concrete mixed design and how it affects or how it can be incorporated in the mixed design of concrete, right? So far we have looked at how do we determine the water cement ratio, water content, cement content, air content, and so on. But in all the three design methods, we never really explicitly considered the packing density and the rheology, which is the flow properties, right? So, but we then looked at in lecture 18 how we will how are these properties for the concrete, and then how we can incorporate that in the mixed design. And in the final lecture for week 6, we looked at the batching and the mixing process for concrete, right? So once you have decided, you have made a design, like, so in the design you come up with the proportions for the different components that make up the concrete system, right? How much cement content should be there, how much water should be added, how much coarse aggregate, fine aggregate, and other admixtures, and so on. So once you have designed it, so you have to go to the field to produce it, right, and use it. So the first step to do that is batching and then mixing. So batching is where we take the appropriate measurements as per our design, and then we go for the mixing, right? So once we have taken the appropriate proportions, how do we mix it to produce concrete? Okay, so that's the concepts that were covered in the 6th week. So we'll look at some problems related to these concepts. Okay, so the first question is, the mixing water requirement is lower for non-air entrained concrete. So that is the statement given. So is this statement true or false? Okay, so we looked at when we are looking at the ACI 211 methods, it gives it talks about non-air entrained and then air entrained concrete separately, right? So this is different from the IS method and the DOE method that we looked earlier, right? So where we did not have any separation between the non-air entrained and air entrained concretes, but whereas the ACI method explicitly talks about these two concretes separately, and also the water requirements are given separately for non-air entrained and air entrained concrete. So this question is saying that the problem statement here is that the mixing water requirement, when you compare it with air entrained concrete, it is lower for non-air entrained. Okay, so we have to pick whether it is true or false. We will create a poll as usual. So you can answer in the poll whether if you think whether it is true or false. Okay, the poll is launched. You will be able to find the poll within the activities option. So if you open activities, you'll find the polls, and you can pick one option, A or B. Okay, so we have one vote for option A, true. Okay, so now let's look at the answer. The answer is actually option B, false. Okay, so if you, so I have given the taken the water content table that was provided to us in the lecture. Right, so this is coming from the ACI method. So the left hand side table gives us the water content for non-air entrained, and the right hand side table gives us for the air entrained concrete, right? So for each type, so the water content is actually dependent upon the slump or the workability requirement and also the maximum size of aggregate. So you compare for a given slump range, and also a given maximum size, you compare for non-air entrained and air entrained concrete. For example, let us take 9.5 mm maximum aggregate size and 2.5 to 5 mm or 5 centimeter of slump. We see that for non-air entrained it is 207 kilograms per meter cube, whereas the corresponding value in the air entrained case is 181. See, for the air entrained concrete it is lower. Similarly, for all the other categories as well, other combinations of the aggregate size and the slump ratio, slump requirement, we see that for non-air entrained concrete it is higher, whereas for air entrained concrete it is lower, right? So therefore, the statement says the water requirement is lower for non-air entrained concrete, right? So this is actually the opposite of what we actually have, right? For air entrained it is lower, whereas for non-air entrained it is higher, right? Therefore, the statement is false. So the right option is B, right? So why is it actually lower for air entrained case? Because the air entrained concrete, but because of this air entrainment, the workability of the air entrained concrete will be higher, right? Therefore, you reduce the water content because you are having additional, the workability is actually increased because of the air entrainment. Therefore, you reduce the water content accordingly, right? So that's why for air entrained case, it will be lower. For non-air entrained case, you have to have higher water content. Okay, so moving on to question number 2. As the fineness modulus of sand increases, the per unit volume of coarse aggregate decreases. Again, we have to check whether the statement is true or false. Let me create a poll again. The poll is launched. When the fineness modulus of sand increases, what will happen to the proportion of the coarse aggregate in the unit volume? So here the unit volume is the unit volume of the concrete itself, right? So it's not as a percentage of the total aggregate volume, but it is for the whole concrete mix. Okay, we have one vote for option A, true. Okay, let's look at the answer. The right answer is true, right? So which is when you have coarser sand, right? So fineness modulus is higher means what? What is fineness modulus? So we saw this when in the module on aggregates, right? So the fineness modulus is like approximately like it gives you the average size of the aggregate, right? But it's not going to directly give you the average size. It is close to that. It's like a proxy for that because it tells us the average uh, sieve number, right? So if you have the for each sieve size, if you assign a number in increasing order, so this fineness modulus will give you the average sieve number. So that is approximately gives you an idea of the average particle size, right? So when we say the fineness modulus increases, it means that we'll have larger sized sand particles, right? There are more coarser sand particles. Therefore, what happens to the coarse aggregate volume? Because the sand has a better gradation now, right? So therefore, you will need lesser amount of coarse aggregates, right? Therefore, the given statement is true. Again, this table was given from the ACI method. So depending on the maximum aggregate size and the fineness modulus, we the table gives us what is the volume of coarse aggregate per unit volume of the concrete, right? So let us pick one particular size. So we can say 9.5 mm, and we see for the column, different columns gives us the value of the coarse aggregate content for a different fineness modulus. We see as the fineness modulus increases, the percentage of the coarse aggregate content decreases, right? So 0.5 for 2.4 at 0.44 for 3, right? So therefore, when you have coarser sand, so fineness modulus is higher, your coarse aggregate volume will reduce. Okay. So question number 3, a numerical. So the cement that we are using is OPC, and the fineness modulus of sand is given as 2.6. The density of water used is 1000 kg per meter cube, and the dry roded bulk density of coarse aggregate is 1700 kilogram per meter cube. The maximum size of aggregate used is 25 mm. The aggregates are rounded, and the slump required is 80 mm. No air entrainment is used. So using the ACI mixed design method or the mixed proportioning method, we should determine the coarse aggregate content in kilogram per meter cube of the mix. Okay, so this data is given to us, which we saw in the previous question. What is the percentage or the volume of coarse aggregate per unit volume of concrete? Okay, so we should use this data, and then for the given information, we should find out what will be the coarse aggregate content in per unit volume of the mix. Okay, so maybe you can take 1 or 2 minutes to think through and then solve it. When you are ready, you can use the chat to uh, give your answer, and then we'll look at the solution. If you have any doubts or you need some clarification, you can again ask, unmute yourself and ask, or use the chat. Okay, do we have an answer? Can we go to the solution now? Okay, I think we can take a look at the solution now. Okay, so what do you want to do? We want to determine the coarse aggregate content, right? So in kilogram per meter cube of the mix. So if you take 1 meter cube of the concrete mix, then what will be the content of the coarse aggregate in terms of its mass, right? How much kg of coarse aggregate will be present in 1 meter cube of the concrete, right? So that is what we want to determine. So what are we given with? So we are given with this table which tells us for a given fineness modulus and a given maximum aggregate size, what is the volume of the coarse aggregate in unit volume of the concrete, right? So, so for us, the fineness modulus of sand is 2.6, and the maximum size of the aggregate used is 25 mm, right? So if you look at it, so for 2.6 we'll use this column, and then for 25 mm of maximum size we'll use this particular row. Therefore, the maximum or the volume of the coarse aggregate is 0.69, right? So this is 0.69 per unit volume of the concrete. So that is the first piece of information that we derive. So the volume of coarse aggregate Ca per unit volume of concrete mix is 0.69, right? So we just use the given piece of information on the fineness modulus and the maximum size of the aggregate to derive this, right? So we got it. So it will be 0.69 meter cube, right? So this is fine. Now, but what do you want? We don't want the volume. What we want is the coarse aggregate content in kilograms, right? So how do we get that? We are also given what is the dry roded bulk density of the coarse aggregate, right? So that is 1700 kilogram per meter cube, right? The question is not asking this, right? So we want in kilogram per meter cube, and it is given as 1700 kilogram per meter cube as the bulk density. But this 1700 is not what is asked in the question, right? So this, what is this 1700? If you take 1 meter cube, and if that 1 meter cube is of volume is containing only the coarse aggregate, then the mass or the content will be 1700 kilogram, right? 1700 kilogram in 1 meter cube volume, if that whole volume is occupied by the coarse aggregate, right? But here the volume of 1 meter cube that we are talking about is of the whole concrete mix. So we other components are also there: water, cement, fine aggregates, air also, right? So, so in that case, it will be lesser than this, right? So the volume occupied in that will be lesser. So that is what we have found out now. It is only 0.69 meter cube, right? So it's not 1 meter. In 1 meter cube of the concrete mix, only 69.69 meter cube is occupied by the coarse aggregate. So in that case, then the bulk density is what rho. Let us use the symbol rho. It is nothing but mass by volume, right? So then the mass in a particular volume will be given by rho times V, right? So the bulk density is given to us. It is 1700. It is 1700 kilograms per meter cube times what is the volume that we are talking about? It is only 0.69 meter cube, right? So it is 0.69 meter cube, right? So if you solve this, it will be coming around 1173, right? So this much kilograms of the coarse aggregate will be present in 1 meter cube of the concrete mix. Okay, that is the final answer, 1173 kilograms. Any questions? Was that clear? Okay, so if there are no questions, we'll move on. Okay, so question number 4 is the minimum paste content must account for void content and more to account for dash and dash by 3 to 10%. So again, we can type in what should be the answers. Take a minute to think, recall. So the minimum paste content that we should have in the concrete mix, it should account for the void content definitely, but it should also be increased by 3 to 10%. In addition to this void content, whatever is required for this void content, that should be increased by 3 to 10 percentage to account for what effects. Any answers? Yeah, this is the wall effect and the loosening effect, correct? Right. So to account for the wall effect and the loosening effect, right? So remember, so we find out the approximate void content, right? So we saw in the from the aggregate, the module on the aggregate, the case of a binary mixture, right? And what did we see in that? Okay, so if we have, so here let us say we have purely everything is containing only mixture A, and then we have only mixture B, or a mixture containing only uh, aggregate type B, right? And a mixture containing only aggregate type A. And let us say we are plotting the void content, right, or the void ratio. Then what did we see? We derived a relationship that was something like this, right? So uh, as you increase the proportion of B that is added to A, then the void content was reducing, right? So similarly, on the other case, when you started with B and then you slowly increase the percentage of the aggregate type A, then again we saw the void ratio was decreasing, and we saw that there was some optimal place or optimal fraction where the void ratio was minimum, right? So this optimal, let us just marking it by an asterisk, right? So that was the so there is some proportion, right, of the two mixtures of the two aggregate types. So that will give you the minimum void content, right? But in reality, we saw that this was a theoretically derived, but in reality, we said that the actual relationship will be something like this, right? So it will not be varying like this. It will be varying somewhat like this, right? The optimal proportion will still remain the same, but the void content that is obtained at the optimal position, that is obtained at the optimal fraction will be slightly higher, right? So this is what is obtained in reality, R, and this void content is what is obtained theoretically, okay, T. So we see that in reality, we'll have a slightly higher void content than what we observed or what we derived theoretically, right? So, but the fraction remains the same, optimal fraction, but there is a higher void content, right? It is still minimum for that relationship, but it is slightly higher than what we estimate, right? And this difference or this increase R minus T, right? So this is the delta that we did not that we missed from our theoretical relation, right? So this increase is because of two reasons. One was the wall effect, the other was the loosening effect, right? Because these two are because of particle interference. So when you have different sizes of aggregates, right, then near one, so when there is one type of particles that are adjacent or near to a particle of a different size, and along the boundary, so you will have a lesser packing than what you will observe elsewhere, right? So that is the wall effect. And then similarly, we had the loosening effect where when there is one small size particle that is occupying the void created by some other larger size particle, right? So the packing in that local region will also be somewhat lower, right? So that was the loosening effect. So because of these two effects, we generally have we observe a slightly increased void content, right? Therefore, the paste content that we are calculating should be will be based on this void content that we are theoretically deriving, and then we increase it by some percentage, typically 3 to 10. Therefore, accounting for the increased void content that we will see in reality. Okay, any questions? Okay, so there are no questions. We'll move on. So question 5 is a good water reducing agent should produce minimum flow with the highest dose. Okay, we should tell whether the statement is true or false. Okay, I'll create a poll for this question. Okay, I have launched a poll. WRA is water reducing agent. Okay, we have one vote for option A. Any other answers? You'll find the poll option, feature within the activities. Okay, we'll look at the answer first. The right answer is option B, false. Right. Right. So here we have the graph shows the dosage. What is the flow produced through different dosage of superplasticizers? Right. So different curves show different superplasticizers, and then how the flow is affected by the dosage. Right. So we see that for different superplasticizers, as we go beyond certain threshold, right? So it depends on the superplasticizer as well, but there is a threshold beyond which increasing the dosage will not give you more flow, right? So there is some saturating value of flow that you will attain, beyond which increasing the dosage of the superplasticizer will not have any effect, right? So, but you see that there is some for each plastic superplasticizer, there is some optimal dosage where you get the maximum flow, right? And what is the question saying? It is saying that a good water reducing agent should produce minimum flow with the highest dose. So this is false for two reasons. One, what is the purpose of adding a water reducing agent? So it is to increase the workability, right? So which means that you should have higher flow, right? So a good water reducing agent should provide you with higher flow, right? And also with not with the highest dose, with some so with higher dose we see that the flow does not generally increase, and it will also be higher. So at higher dose the flow will not be lower, it will be higher. So therefore it is wrong from those two aspects. One is at higher dose you will not get the minimum flow, you will have the higher flow, and also you do not want to produce minimum flow, but you want to get more flow with a water reducing agent, right? So because of that, this statement is false. Okay, any questions? Okay, we'll move on to question number 6. Which of the following is more preferred for large concreting jobs? A. Volumetric batching. B. Wave batching. Okay, the poll is launched. Okay, we have one vote for option B, wave batching. Okay, the right option is also B, wave batching. Okay, so we looked at two different ways of doing the batching, right? So one was the volumetric method, other was the weight-based method, right? And what is preferred for large concreting jobs and for all uh, engineered structures is the weight-based method, right? So that is what we prefer. Whereas volumetric matching is an older technique, right? And it is only used when you are going for non-engineered or small jobs, right? So why is that the case? Because in a volumetric batching, it is the volume, you take a fixed volume container, right? And then you try to fill or take the material by filling that container of that fixed volume. But but the amount that you take, right? If you look at the mass that you are going to take by filling that volume or fixed volume, is going to depend upon how well it is, how well the content you are taking is packed, right? So if you are loosely packing it, you can still fill up the volume, but the mass that you are going to take will be lesser, right? So if you are going to densely pack it, then for the same volume you could get more mass, right? So therefore you will have lesser control, right? And therefore it can lead to more variations when you are going for volumetric batching, and therefore it is easier to deviate from the mix proportioning, right? So that you have lesser control. Whereas as opposed to volumetric batching, in the case of weight batching, you're going to measure it by mass, right? So therefore you will have better control. You will be able to more precisely stick to the mix proportioning that was designed, right? Therefore you will have more control and therefore lesser variation in the proportioning of the different components that you are going to include in the concrete mix, right? So therefore you will have better strength and lesser variation in the strength, right, through weight batching, right? So that's why the weight batching is more preferred when you are going for large work. Okay, so question number 7 is, as per IS 456/2000, what is the minimum mixing time for concrete? So the options are 1.5 minutes, 2 minutes, 2.5 minutes, and 1 minute. Okay, we have one more for option A, 1.5 minutes. Okay. The right option is option B, 2 minutes, right? So this is as per IS 456, right? So if you remember, IS 456 2000 gives us a single value of mixing time, right? So that is, it specifies that an overall minimum mixing time of 2 minutes should be used, right? So this is the minimum mixing. So you should not mix under 2 minutes, right? So you could do more than two, but it should not be lesser than 2 minutes, right? So that is as per the IS 456 2000 guidelines. The IS 49525 1968 is also it also gives us mixing time, but that is dependent upon the capacity of the mixer, right? So it gives us different values for different mixer capacities. Whereas IS 456 gives us a single value, which is minimum of 2 minutes, right? So therefore the right option is B. Okay, so question 8 is, how is the water to cement ratio for a concrete mix determined? Option A, workability. Option B, strength and durability criteria. Option C, maximum size of aggregate. Option D is density of concrete. Okay, so we have one answer for option A. The right option is actually option B, the strength and the durability criteria, right? So if you remember from our earlier lectures on the IS method, DOA method, so there we said that we have two different ways of picking up the water cement ratio, right? So one is coming from the strength that you need. So we will look at the target mean strength, right? And then what is the water cement ratio that will give us this target mean strength, right? So we already saw that the water cement ratio is one of the key components that will affect the strength of the concrete, right? So a lower water cement ratio is generally preferred to attain a higher strength, right? So because when you add more water to it, to the concrete, thereby the water cement ratio becoming higher, you will reduce the strength because you will be increasing more capillary porosity, right? And those pores will not be contributing to the strength, right? And therefore the water cement ratio is one important criteria which will determine the strength of the concrete, right? So through a strength requirement, the water cement ratio will be decided. But there is also the durability requirement, right? So the durability criteria will tell you the durability criteria has multiple components. So one of that is the water to cement ratio. So there is a maximum water to cement ratio that is specified as a part of the durability criteria, right? So there will be also the minimum cement content and so on, right? So water to cement ratio is decided based on the strength criteria and the durability criteria, right? And the minimum of the two, right? So strength for the required strength, you will have one water to cement ratio, and for the durability requirement, you will have one maximum water to cement ratio. And the minimum of these two will be the final water to cement ratio that you will go for when you are going for the trial mix, right? Therefore, the right option is B, the strength and the durability criteria. Whereas the other options, the workability, the maximum size of aggregates, so these do not influence the water to cement ratio directly, but they will affect other properties. Okay, so therefore, the right option is B, the strength and durability criteria. Okay, any questions? Okay, moving on to question number 9. Which of the following determines the water content for a concrete mix? So the options are maximum size of the aggregate, shape of the aggregate, workability, D, all of the above. Here the poll is launched. Okay, any questions? Any answers? Which of the following do you think will decide the water content? So earlier we saw the water to cement ratio. Here we are talking about the water content. Any answers? Shall we look at the right option? Okay, so we'll take a look at the right option now. So the right option is actually all the above. So maximum size, shape, as well as the workability, all three of them will affect what is the water content that is required. So is that so maximum size of aggregate. So when you have a larger maximum aggregate size, right? Your water content. So when your MSA is higher, so let us say property, and then your water requirement, right? So when you have larger maximum aggregate size, right? So your water content requirement will go down. Why? Because when you have a larger maximum size, which means that you are having a large range of sizes, right? So your gradation, aggregate gradation is better. So you have many different sizes available, right? So that's why you are going for a higher maximum aggregate size, right? Therefore, what does that mean? When you have a better gradation, different sizes that are available, which means that there will be better packing, right? So we saw how the voids created by a larger sized particle will be occupied by a smaller sized particle, right? So because of that, your voids will go down, and you will get a better packing, right? Therefore, your water content requirement will go down, right? Because you have lesser voids now. So the maximum size will affect the water content. The shape of the aggregate, again, this is related to what again, what will be the packing, right? So we saw that for rounded aggregates, spherical or rounded, you will have the highest packing, right? So for that, you will need lesser water. Whereas if you have angular aggregates, right, there will be more voids now, and then it will increase the water content that you require, right? If you look at the codes, you will generally see that different water content tables will be provided uh, depending on the type of aggregate that you are using, right? So whether you have crushed aggregate or rounded or angular, right? So therefore, the shape of the aggregate will also affect your water content, like your maximum size. And then the workability requirement, whether you want higher slump or lower slump, right? So it could be defined in terms of slump or in terms of VB time or so on, right? So there are different metrics that is used to measure workability, but whatever is it, the workability requirement will also determine the water content that you need, right? So if you need a higher slump or higher workability, you will need higher water content as well, right? So that is the trend that you will see, right? Because all the three effects, the right option is all the above. Okay, any questions? Okay, so moving on. Question number 10, a numerical problem. So the desired 28-day cylindrical compressive strength of a concrete mix is 25 MPa, where no air entrainment is to be used. The cement used is OPC. The MSA maximum size of aggregate is 19 mm, and the desired slump is 80 mm. Find the cement content as per the ACI method. Right. So, and then three tables are given. One is for the water content, the other is for the average or determining the average strength, and the third one is for estimating the water to cement ratio that is required. Okay, so you can take a couple of minutes. Okay, if you have any doubts, you can ask, and then when you are ready, you can use the chat. Then we will look at the solution. Okay, do we have an answer before we look at the solution? Okay, so let's take a look at the solution now. Okay, so the question is to find out what will be the cement content. Okay, if we design it using the ACI method. Okay, so we know the 28-day cylindrical compressive strain, the whether we have an air entrainment or not, the type of cement, the MSA, and the desired slump. Right, so this is the information that is given to us. Right, so there are basically four steps to determine the cement content. Okay, so the first step will be to find the water content. Okay, the second step is to determine the average strength, right? And third step is to find out the water to cement ratio for the above average strength. And the final step is to calculate the cement content. Okay, so these are the steps that we need to follow. Okay, so the first step is to find out the water content. Okay, how do we get the water content? So for water content, again, it is dependent on whether you have air entrainment or not, right? So this, in this case, we are not using any air entrainment, and the corresponding table from the ACI standard is given to us, right? And for getting the water content, we need two information. One is what is the slump requirement, and what is the MSA that we are using, right? So those two are given to us. The slump used or the desired slump is 80 mm and the MSA is 19 mm, right? So for 19 mm MSA, we should use this column. And then for 80 mm, which is 8 centimeters, right? So we should use this particular row, 7.5 to 10. So based on that, if you look at it, the water requirement is 205 kilograms per meter cube, right? So directly we can get it from the table, right? So the water content is straightforward, right? So the water content is 205 kilograms per meter cubed. Okay. So that is the first step. So the second step is to determine the average strength. Okay. How do we get the average strength? For the average strength, so we have three different relationships that is based on the 28-day compressive strength, right? So the desired 28-day compressive strength for the cylindrical specimen. Right? So this is the difference that we see between the ACA method as opposed to the IS method and the DOE method, right? So in the IS and the DOE method, we were using cubical samples, right? Whereas in the ACI method, we are using cylindrical samples, right? And therefore, and also we are given with different relationships for determining the average strength for a given desired cylindrical strength for at the 28 days, right? So if it is less than 20.7, we use this relation where FCR is equal to FC plus 6.9. If it is between 20.7 and 34.5, we use this one. And if it is 34 greater than 34.5, we use the third relation, right? So this is in the case where we do not know the standard deviation of the strength variation. In that case, we can use these relations, right? So in this question, since we do not know the standard deviation of the strength variation, we go with the given equation. So we should determine what equation to use. For that, we will choose the one based on the 28-day still compressive strength that we require, right? So we require 25 MPa, right? And that is falling in this range between 20.7 and 34.5. Therefore, the equation that we will use is the second one, FCR equal to FC plus 8.3. Okay, so FCR equal to FC plus 8.3. Okay, so FCR is the average strength and FC is the desired strength, which is 25 MPa. 25 plus 8.3. Okay, so that is the relation that we will use. So that will give us, so this is the average strength that we will design for. Okay, 33.3 MPa, right? In the IS method, it will be the characteristic strength plus 1.65 times the standard deviation, right? So whereas here we will use this relation. Okay, so that we got the average strength. So second step is done. So the third step is to find out the water to cement ratio that will give us this average strength that we have calculated. How do we get that? So we'll use this third table where for different cylindrical compressive strengths, we are given what is the water to cement ratio that we should take. Again, for non-air entrained and air entrained separately, right? So since we are dealing with non-air entrained, we'll use this column, but we have only the values for three different strengths given to us, right? So for 25, 40, and 45, but the strength that we want is 33.3 MPa, right? Therefore, what we will do is we will use linear interpolation to find out what will be the water to cement ratio that we should use for 33.3 MPa, right? So, let's see. So, we needed for some y, uh, which is what we want to find out water to cement ratio. For 25 MPa, it is 0.62. Okay, so y minus 0.62. So by we need it for 33.3 minus 25. Okay, so this will be equal to, so we know the values of the water to cement ratio for 40 MPa and 25 MPa, right? So 0.43 for 40 MPa and 0.62. So it will be equal to 0.43 minus 0.62 divided by 40 minus 25. Okay, so if we solve this, we will be able to find what y is. Okay, y comes out as 0.53. Okay, so we have used linear interpolation to find out what is the water to cement ratio corresponding to 33.3 MPa. Okay, so we know the values for 40 and 25, the corresponding water to cement ratio. So using that, we assumed a linear relationship between the strength and the water to cement ratio and obtained the water to cement ratio for corresponding to 33.3 MPa. Okay, so that is 0.53. So step 3 is done. The final step is to use the water content and the water to cement ratio to obtain the cement content. Okay, so cement content would be nothing but the water content divided by the water to cement ratio. Okay, so water content is 205 and the water to cement ratio is 0.53, right? So therefore the cement content is approximately 387 kilograms per meter cubed. Okay, so that's how we calculate the cement content using the ACA method. Okay, any questions? Okay, let me just repeat the steps that we followed, right? So we were given the desired 28-day strength whether we use air entrainment or not, the type of cement, MSA, and the desired slump, and we wanted to find out the cement content. So the first step we did was find out what is the water content required, right? So for finding out the water content, we use the table, right? So for the given maximum size of aggregate, for which is 19, and the slump requirement, which was 8 centimeters, we found out that the water content required is 205 kilogram per meter cube. The second step we followed was determining the average strength. So the average strength is related to the desired strength uh, by three different equations depending on the desired strength that we need, right? So for 25 MPa, it is given by Fc plus 8.3, right? So we use that Fc plus 8.3, which is 33.3 MPa, right? So and that is the desired that is the average strength that we will design for. And then once we have the average strength, we need to find out the water to cement ratio that will give us this average strength. So the water to cement ratio is given for different compressive strengths, right? For non-entrained, non-air entrained, and air entrained. So for the strength that we require, we use linear interpolation to find out what is the water to cement ratio that is required. So which came out as 0.53. And then using the water content that we derived earlier and the water to cement ratio, we found out that what is the cement content that is required, right? So that is how we use the ACE method for finding out the cement content. Okay, and there is no question. We'll continue. Okay, so question 11 is, which of the following affects the workability of concrete? So the options are paste content, water content, superplasticizer, and all of the above. Okay, a poll is created. Can make use of it to answer. Any answers? Okay, so let us take a look at the right option now. So the right option is option D, all of the above, right? So all the three, paste content, the water content, as well as the superplasticization will affect the workability, right? So we saw that uh, in, in one of the lectures, right? So how much are we going to add the cement paste? How much water we add? Also the dosage of the superplasticizer. So what is the effect that we will see? So when you have more paste content, right? So your workability, let us say, so the effect on workability will be it will reduce your workability, right? When you have higher water content, your workability will increase. And superplasticizer, we saw in one of the earlier questions, right? So you have higher dosage of the superplasticizer, your workability will increase, right? So all the three affects your workability, and the trend is as given here. So generally for water content alone, we have seen in the earlier sessions as well. So when it is not really desirable to increase your workability beyond a certain limit using by increasing the water content. Why? Because uh, that excess water that you are going to add will actually reduce your strength, right? So because it is going to increase your water to cement ratio, and therefore it will, even though it provides you walkable concrete, it will contribute negatively to the strength, right? So that is one point that you should keep in mind. Okay, but other than that, here talking only about the workability, all the three will affect it. Water content and superplasticity positively and paste content negatively. Okay, any questions? Okay, so moving on to question 12, another numerical. So again, we'll be using the ACA method now. So the desired 28-day cylindrical compressive strength of a concrete mix is 35 MPa, where no air entrainment is to be used. The cement used is OPC. The fineness modulus of sand is 2.6. The specific gravity of fine aggregate, coarse aggregate, and cement are 2.7, 2.6, and 3.15 respectively. The density of water used is 1000 kilograms per meter cube. The dry roded bulk density of coarse aggregate is 1700 kilograms per meter cube. MSA of rounded aggregate 19 mm. Desired slump 80 mm. The minimum cement content and maximum allowable water to cement ratio from a durability perspective are 300 kilograms per meter cube and 0.5. Standard deviation of the whole set of samples is 4, and we want to use the ACA mix method to determine the 4 quantities, which are the free water content to be used in the mix in kg per meter cube of the mix, the air content in percentage by volume, the mean compressive cylinder strength in MPa, and the water to cement ratio that will give the main compressive cylinder strength that we calculated. Okay, maybe you can follow the similar steps that we adopted when we found out the cement content, right? But we have to do more here, but we can follow similar steps. And yeah, I'll give you maybe 2 or 3 minutes. You can take it to solve it, and then we'll look at the solution. If you need the tables, it will be the same as earlier. I can show you the tables. So same tables as earlier. So whenever you need it, you tell me, I can switch to that slide. Okay, any answers? Shall we look at the solution now? Okay, so let's look at the solution now. So it is the same procedure, right? So we are using the same method, ACA mixed design method. So the same steps, but here it is one step lesser because we need to find only until the water to cement ratio part, right? So we are not looking for the cement content here. So until water to cement ratio only we have to do. So the last step that we did to find the cement content, that is not required here. So basically the same thing. The steps. So the first step is to find the water content, right? But here, in addition to the water content, we also need to find the air content, right? So that is still in the step one. So step two is to find out the average compressive strength. Step three, find the water to cement ratio, right? So the same procedure we'll follow. So the first step is to find the water and the air content, right? So those are the first two questions. How do we find the water content? So we use the slump requirement as well as the MSA, right? So the same table will go back. So we use the same slump criteria and the maximum size of the aggregate to determine what is the water content, right? So similar to the previous question, so we are using the same maximum size of aggregate and the slump requirement is also same, 8 centimeters. The water content is exactly the same as the previous one, 205 kilograms per meter cube, right? So we are using 19 mm aggregate and 80 mm slump. Okay. So the water content is same as earlier. So water content is 205 kilograms per meter cube. Right now, the second part of that is to find the air content. So again, the air content is given for non-air entrained and air entrained concrete separately, right? So the table here tells us what is given for the non-air entrained, which is what is given in our question. So again, the air content is determined based on the maximum size of the aggregate, right? So we are using 19 mm MSA, therefore the air content is 2%. Okay, so with that, step one is done. So we determined the water content and the air content. So the second step is to find out the average compressive strength. So here we will be slightly differing from what we did in the previous question. So in the previous question, we were directly given with different, the relationship between the desired strength and the average strength, right? So based on what is the desired compressive strength is, right? So and at that time I said this is the relation that we use when we do not know the standard deviation, right? So when we do not know the standard deviation of the strength variation, can directly pick one of these equations based on the criteria here and then use it. But in this particular case, we are given with the standard deviation of the strength variation, right? So the standard deviation of the whole set of samples is 4, right? So when the standard deviation is known, then there is the procedure that we follow is there are two sets of equations. So one, I'm calling it as FCR1 for the first average. So that will be FC plus 1.34S, right? So where S is the standard deviation of the sample. Okay, so that is one. The other relation is I'm calling it as FCR2 for the second average. So that will be FC plus 2.33S minus 3.5. Okay, so we find out these two average values. So from the first relation and the second relation, we'll get two different average strength, and then the final average string that we will use, which is FCR, will be the maximum of these two values. Okay, maximum of FCR1 and FCR2, right? So when the standard deviation is given or known, then this is the procedure that we will follow that to find out the average string, right? So we use the first relation, FCR1 is FC plus 1.34s, the second relation, which is FC plus 2.33s minus 3.5, and then the maximum of these two values will be taken as the average compressive strength. Okay, so from the first one, what we will get, so FC is actually 35, right? So the desired 28-day strength is 35 MPa. So FC is 35 plus 1.34 times the standard deviation is given as 4 MPa, right? So therefore, FCR1 is 40.36. 40.36 MPa. And then if you do it for the second equation, it will be 35 plus 2.33 times 4 minus 3.5, right? And this will give you 40.82 MPa. Okay, therefore the average strength is actually the maximum of 40.36 and 40.82, therefore it is 40.82 MPa. Okay, so that is the second step. We found out the average compressive strength, right? So which is the question 3 here, to estimate the mean compressive cylinder strength. So the final one that you want to find is the water to cement ratio for the corresponding to this compressive strength that is required, right? So that is similar to what we did earlier, right? So we have the water to cement ratio given for non-air concrete at different compressive strengths for at 28 days, and then for us it is 40.8, right? So 40.8 is close to 40, it will be almost close to 0.43. It's again we could do linear interpolation here like we did earlier, and then it will come out as, so water to cement ratio for 40.82 MPa, right? So that if you do the linear, slightly decrease, so from 0.43 for 40, it will become 0.42 approximately for 40.82 MPa. Okay, so that is how we find out the water to cement ratio. Okay, so the same procedure. So first step, finding out the water content and air content. So water content, we use the MSA and the slump requirement to get this water content from the table. The second step is to find out the air content. So air content for non-air concrete depends on the MSA only. So therefore, for a given MSA, the air content is 2%. And then when the standard deviation is given of the strength variation, then we use two different equations to get an estimate. So the first equation is FC plus 1.34s. So that gives us one estimate. The second estimate is given by FC plus 2.33s minus 3.5. And then the maximum of these two estimates will be taken as your main cylindrical strength, okay, which is 40.82 in this case. And then for the given or for the required strength of 40.82, the required water to cement ratio is taken from the table, right? So that is 0.42. Okay, so those are the steps that we follow to find out these values using the ACA method. Okay, so moving on to question number 13. In its fresh state, concrete behaves as a, options are Bingham fluid, Newtonian fluid, none of the above, and Newtonian in the fresh state and Bingham in the hardened state. Okay, so here we are talking about the rheology of concrete, right? How it flows under and when applied when shear stress is applied, right? How does it behave, right? So we have Newtonian fluid, Bingham fluid, and then Newtonian in the fresh and the Bingham in the hardened state. So here we are only concerned with the fresh state, and the answer is that it behaves as a Bingham fluid in the fresh state, right? So recalling the rheology of fresh concrete that we looked at in the lectures. So if you look at it, a Newtonian fluid will have the rate of shear deformation is proportional to or the shear stress is proportional to the rate of shear deformation, right? That is for a Newtonian liquid, whereas if you look at concrete, it behaves like a Bingham fluid where there is a threshold value of the shear stress until which point it will behave like a solid, right? So there won't be any deformation that you will see, right? So until that threshold is crossed, right? So it will behave like a solid. But once that threshold is crossed, then you will see that as the shear stress increases, there will be increasing rate of shear strain, right? And so that is what we call as a Bingham fluid, right? There is some threshold. Once that threshold is crossed, then it will behave like a plastic, right? So you will see deformation. So if you extend this line where it becomes linear, so you will see one particular value of the shear stress, which we call as tau naught. That is the yield shear stress, right? So once you cross that value, it will become like plastic, right? So that is how fresh concrete behaves, and that is what we call as the Bingham model or the Bingham fluid, right? So that is the right option, which is option A. So question 14 is about the mixing time again for concrete for a capacity of 3 meter cube. Right? What is the mixing time of 3 meter cube of concrete according to IS 4925 1968? So the options are 1 minute, 1.5 minute, 2 minute, and 2.5 minute. So in earlier question we saw the mixing time as suggested by IS 456 2000. Now we are looking at IS 4925. So the right option is option C, 2 minutes. So we saw that IS 456 gave only a single value of 2 minutes, whereas IS 4925 gives us multiple values that is dependent upon the capacity, right? So for different capacities of 2 meter cube, 3 meter cube, and 4 meter cube, there are different mixing times that are recommended, right? So for 2 meter cube, it is 1.5 minutes. For 3 meter cube, it is 2 minutes, and for 4 meter cube, it is 2.5 minutes, right? So depending on the mixer capacity, the mixing time varies, right? And the question is for a 3 meter cube of concrete. Therefore, for 3 meter cube, the code suggests a mixing time of 2 minutes, right? So therefore, the right option is C, 2 minutes. So question 15 is, which of the following is not correctly matched? So we have 4 different ingredient quantities like water, paste, GGBFS, which is ground granulated blast furnace slag, and then more water. And then 2 columns that gives us what is the effect on the yield shear stress on the fresh concrete, and what is the effect on the plastic viscosity on the of the fresh concrete, right? So the first match is that less water will increase the yield shear stress and also increase the plastic viscosity. By adding more paste, we'll decrease the yield shear stress and increase the plastic viscosity. So GGBFS, when it is increased, will have a decrease on the yield shear stress and also a decrease on the plastic viscosity. And adding more water will decrease the yield shear stress and also decrease the plastic viscosity, right? So we have to tell us which of the 4 matchings given is incorrect. Okay, so the incorrect matching is option 3, right, which is saying that GGBFS will decrease the yield shear stress and decrease the plastic viscosity. So why is that? So we saw that how will different components will affect the viscosity and the yield stress, right? So looking at water, so when you add more water or when you have less water, then the effect is in this direction where the yield stress will increase and the viscosity will also increase, right? So when you have less water, it will be less workable, right? Less plastic, and therefore your plastic viscosity increases and the yield stress also increases. The opposite effect will be seen when you add more water, right? So your viscosity will reduce and the yield stress will also reduce, right? But whereas for GGBFS, the yield stress will decrease when you add more of it, and then your plastic viscosity will increase. So for paste, when you have lesser paste, you will have lesser viscosity and higher yield stress. The opposite is true when more paste is added. You will have higher viscosity and lesser yield stress, right? So the question, so we looked at water, paste, and GGBFS, right? So the relationship given is correct for water and paste, right? So when you had lesser water, yield stress increases as well as the viscosity increases. When you have more water, the opposite, both yield stress and the viscosity decreases. So paste, when you add more, yield stress decreases, whereas the viscosity increases. But only for GGBFS, the match is wrong. It says that both the stress as well as the viscosity decreases, but we saw that the viscosity increases and only the stress decreases, right? So therefore, the incorrect matching is only 3. Okay, so moving on to question number 16. So here we are given with 4 statements and we have to tell which of these statements are correct. So the first statement is less water content makes the paste softer with greater dispersion of the cement particles. Statement 2 is the dispersion of the aggregates gets reduced when the volume of the paste is decreased. Statement 3 is the paste content, water content and superplasticizer would govern the flow properties of the concrete mix. And the fourth statement is cohesiveness is governed by the tensile strength of fresh concrete. Right? And then we are given with different options. 1, 3, 4 are correct, 1, 2, 3 are correct, 2, 3, 4 are correct, and 1, 2, 4 are correct. So we have to, so from the options, it seems like 3 of them are correct, 1 is wrong. So we need to identify that. Okay. So let's go by statement by statement. So first statement tells us lesser water content makes the paste softer with greater dispersion of the cement particles. So this is actually the incorrect statement, right? So when you have lesser water content, as we saw earlier, we saw that when you have lesser water content, right? So that the yield stress as well as the plastic viscosity will actually increase, right? So therefore, it will not cause it will actually reduce the dispersion of the cement particles, right? So when you have lesser water, we will have lesser dispersion and it will not be softer, right? So therefore, the first statement is not correct, right? You will have a less workable mix because of lesser dispersion actually. The statement 2 is that dispersion of the aggregates gets reduced when the volume of the paste is decreased. That is true. So when you have lesser paste, right? So the coating of the paste on the aggregates will reduce, right? So and therefore the aggregates will not actually uh, will not move away from each other, right? So the dispersion will reduce. So when you have more paste, this paste will try to push the aggregates farther away, right? And therefore you will have better dispersion when you have more paste, more volume of the paste. The third statement is all the three, which are the paste content, water content, and the superplasticizer, governs the flow properties of the concrete mix. So we saw this earlier, right? So the flow properties we talked about, which how will it affect the workability, right? So we saw the paste content will be negatively affecting, right? So when you have more paste content, you will have lesser workability. When you have higher water content, you will have higher workability, and higher superplasticizer, you will have higher workability, right? So it will, all these three will affect the flow properties of the concrete mix. So it is true. Statement 4 is cohesiveness is governed by the tensile strength of fresh concrete. So what do we mean by cohesiveness? It is the homogeneous and the uniform mixture of the components in the mix, right? And also it should not segregate, right? So the component should not move away and then it should not separate from one another, right? So therefore that cohesiveness is governed by the tensile strength. So when you have lesser tensile strength of the fresh concrete, so you will have lesser cohesive concrete, right? There will be more segregation and more bleeding that you will see when the tensile strength is low, right? And vice versa. Therefore, the cohesiveness is actually determined by the tensile strength of the fresh concrete. So this statement is also true. So out of the 4, 2, 3, 4 are correct. 1 is false. So the right option is C, 2, 3, 4. Okay, moving on to question 17. We are given with 2 statements and we have to pick up one of the options here. So the first statement is long mixing time may not increase the strength proportionally and reduction in strength can be seen in some cases. Statement 2 is long mixing time leads to over grinding of the material which results into more fines. Okay, so the first statement is true. So when we mix for too long, right? So we may not see an increase in the strength proportional to the increase in the mixing time. And also in some cases, the strength will actually decrease, right? So initially, when you are mixing for when you increase the mixing time, initially you will actually see a strength increase, and that strength increase is due to better mixing, better homogeneous distribution of the aggregates and the cement paste, right? So because of that better homogeneity, you will see an increase in the strength when you increase the mixing time. But when you are going to mix it for too long, the strength increase will actually it will not keep on increasing forever, right? So it will actually the strength increase that you will see will actually start going down. And if you are going to mix for even further time, right? So then you may also see some reduction in the strength also, right? So that relationship given here is true. And statement 2, if you look at it, it says that long mixing time leads to over grinding of the material, which results into more fines, right? So that is also true when you have when you mix for longer, and because of the aberration, you may find that the aggregates will get ground, and then you will find more fines result in the resultant mixture, right? Therefore, what that will do is, which is exactly why the strength reduction that we are saying happens, right? Because of the introduction of more fines due to longer mixing, will actually be reducing the strength, right? So therefore, the two statements are true, and the reduction in the strength part is actually explained by the statement 2, right? So the right option is option C. Both the statements 1 and 2 are correct, and the second statement is the correct explanation for the statement 1. Okay, so question 18 is, according to IS 4295, which of the options given below are correct or is correct about the batching tolerances of the ingredients, which are cement, water, aggregates, and admixtures respectively. So we have given different tolerances, right? And then for cement, water, aggregate, and admixtures, and then which of these is correct as per the IS 4295 code. So the right option is option B, 1% for cement, 1% for water, 2% for aggregates, and 3% for admixtures, right? So this is given in IS 4925 for batching. So there is a higher or a lower tolerance or higher accuracy is necessary, or higher quality control is necessary when we are batching cement and cementitious material and water, right? So why? Because this is understandable, because the water to cement ratio governs your strength, right? And strength and also your durability, right? So therefore, the tolerance is much lower for cement and water, which is 1% plus or minus 1%. Whereas for aggregates, 2% is allowed plus or minus, and for admixtures, plus or minus 3% is allowed by the code. Okay, so that is for the batching part as given by IS 4925. Right option is option B. So it was given in this order: for cement, then water, then aggregates, and finally for admixture. Okay, so question 19 is another design question. So where we want to design a 30 MPa cylinder strength concrete mix with a standard deviation of 5 MPa. Right? The cement type that we are using is OPC. Extreme exposure conditions. The fineness modulus of sand is 2.6. The specific gravity for the fine aggregate is 2.7. The slump requirement is 80 mm. We are using non-air entrained concrete, 19 mm MSA, which are rounded, and the dry rodded bulk density of the coarse aggregate is 1600 kilograms per meter cubed, and the specific gravity for the coarse aggregate is 2.6. Again, we will be using the ACI 211 method to solve this problem. Okay, and then we are given with these tables. So the first table gives us the water content in kilograms per meter cube for depending on the slump and the maximum size of aggregate. Then the air content based on the maximum size of aggregate, and the coarse aggregate volume per unit volume of the concrete mix depending upon the MSA and the fineness module of sand, and also the water to cement ratio as a function of the cylindrical compressor strain. Okay, so this is the information given to us. So we'll follow the same method to determine or to design this. So when you want to design it, what are the things that you want to find out? So you want to find out what is the water content, air content, what is the water to cement ratio that we'll use, the cement content, and also the content of the coarse aggregate and the fine aggregate, right? So the proportions of all this is needed to be found out. Okay, so the first step that we follow is to find out what is the water and the air content. Okay, so let's start with the air content. So for ACI method gives us the air content for the non-iron trained concrete as a function of the maximum aggregate size. So we are using 19 MSA rounded aggregate. So corresponding to that, the recommended air content is 2%, right? So it is in percentage. So it is directly taken from table as 2%. So next we will determine what is the water content. So for water content, so we need to know the MSA as well as the slump required, right? So MSA is 19 mm and the slump requirement is 80 mm, which is 8 centimeters. So it is in the range of 7.5 to 10. So we will use this row and this column, so which gives us a water requirement, water content of 205, right? So water content is 205 kilograms per meter cubed, right? So that is the first step to determine the water and the air content. The second step is to find out the mean compressive strength, right? So for this, because we know the standard deviation, right, so which is given as 5 MPa, so we will be using the two relations that we saw earlier and then take the maximum uh, of the mean strength given by the two relations, right? So the two relations are, so FCR1 was FC plus 1.34 S, and the second relation was FCR2 was FC plus 2.33 S minus 3.5, right? So we'll find these two. So for the first one, FC is 30 MPa, right? So we want 30 MPa. So 30 plus 1.34 times standard deviation is 5 MPa, right? So that will give us 36.7 MPa. And then for the second relation, it is 30 plus 2.33 times 5 minus 3.5. So that will give us 38.15 MPa, right? So finally the average strength that we will design for is the maximum of these two, right? So maximum of FCR1 and FCR2, right? So that is 38.15 MPa. Okay, this is the second step, which is to find out the average compressive strength for the cylindrical or the average cylindrical compressive strength. Okay, so the third step is to find out the water to cement ratio. So how will we find the water to cement ratio is based on the estimated mean strength, right? So which is 38.15, right? So again, the table gives us only three distinct values, one for 45, 40 and 25 for non-iron trained concrete. So but we want it for 38.15, right? So it will be between 0.42 and 0.61. Again, we will assume a linear relationship and then use linear interpolation to find out the value corresponding to the strength of 38.15 MPa. So if you do the interpolation, you will find out that it will be 0.45, right, for 38.15 MPa. Okay, so that is the third step. So once you know the water to cement ratio, we already estimated the water content. We can find out the cement content using that. So cement content will be the water content divided by the water to cement ratio, right? So which is 205 by 0.45. So that will give us approximately approximately 456 kilograms per meter cubed. Okay, so we found out the air content, water to cement ratio, and cement content. What's left is the aggregate, right? So what will be the coarse aggregate content and the fine aggregate content? So how do we find that? So to find out that, so we'll start with the coarse aggregate, right? So we are given with this information, right? For different fineness modulus and different maximum aggregate size, what is the coarse aggregate content in what is the volume of the coarse aggregate in one in per unit volume of the concrete mix, right? So for 19 mm MSA and the fineness modulus is 2.6, right? So for 19 mm and 2.6, the value is 0.64, right? Which means in 1 meter cube of the concrete mix, 0.64 meter cube will be occupied by the coarse aggregate, right? So the volume of coarse aggregate per unit volume of mix is equal to 0.64 meter cubed. Okay, so we know the volume in 1 meter cube of the concrete mix, right? So next, how will we find out the coarse aggregate content? So Ca content, coarse aggregate content is so we are also given with the dry roded bulk density, which is 1600 kilograms per meter cube, right? So for the given volume, we can find out what will be the content, right? So it will be nothing but the volume multiplied by the dry roded bulk density, which is 1600 kilograms per meter cube. So the cement, the coarse aggregate content will be 1024 kilograms per meter cube. Okay, so in 1 meter cube of the concrete mix, we'll have 1024 kilograms of the coarse aggregate. So now to find out the fine aggregate, since we have only one component, which is a fine aggregate left, we'll use the conservation of volume. Okay, so for a unit volume, so we have so it is occupied by water, cement, the air content, and also the coarse and the fine aggregates, right? So if we sum up all those volumes, it should give us 1, right? Uh, so if the volume, because the volume is conserved. So for the water, the volume occupied by it is 205 divided by 1000 kilograms per meter cube for water, and for cement it is how much, 456 by 3150, right? And for and then we have air 2%, so 0.02. So this 2% is 2% by volume, right? So 2% of the volume is occupied by air, so it is 0.02 plus the coarse aggregate. For coarse aggregate, it is 1024 is the content. So divided by, so its specific gravity is given as 2.6. Okay, so it will be 2600 plus fine aggregates. We don't know its content, so we'll keep it as Fa divided by the specific gravity for that is 2.7. So divided by 2700. Right, so therefore the only unknown here is the fine aggregate. So by solving this, we'll find out that the fine aggregate content will come out as 638 kilograms per meter cubed. Okay, so with that, we now know the proportions of all the components, right? So in 1 meter cube, right, of the concrete mix. So we are done with the design, right? So we'll just recap of what we did. So we wanted to use the ACI method for designing this. So therefore, it was given the desired strength in terms of a cylindrical specimen, right? So we wanted a 30 MPa cylinder strength, and also the standard deviation was given to us. The different, what is the cement type exposure condition, the fineness modulus of the sand used, the slump requirement, non-air entrainment, and also the MSA and the bulk density of the coarse aggregate were given. And so the first step that we did was to find out the air content, so which is for non-air and train concrete, for a given maximum size of the aggregate, we'll get it as a percentage by volume, right? So for 19 mm MSA, it is 2% by volume, right? So we got it. The second step was to find out the water content. To determine the water content, we need to know the MSA, also the slump requirement. So based on the MSA of 19 and the slump requirement of 8 pm, we found out that the water requirement is 205 kilograms per meter cube. And the second step is to find out the mean compressive strength for the cylindrical specimen. And for that, when the standard deviation is known, we'll use two different equations. So the first equation is Fc plus 1.34s, where S is the standard deviation and Fc is the desired 28-day strength. And so that will give us one value. And the other equation is Fc plus 2.33s minus 3.5. So that will give us one other value. And the final value that we will go with is the maximum of these two, right? So in our case, that came out as 38.15 MPa, right? So that completes our step 2. So once we know the mean strength, mean compressive strength that we want to design for, then we use that to determine what is the water to cement ratio to be used, right? So for non-air and train category, for different cylindrical compressive strength, we know what is the water to cement ratio to be used, and therefore for the required strength of 38.15, we determine through linear interpolation that 0.45 is the water to cement ratio. So once the water to cement ratio is known and the water content that we already calculated, we find out what is the cement content, right? So it will be the water content by the water to cement ratio. That will give us the cement content that is required, so which is 456 kilograms per meter cube. And once we know the cement content, then we can move on to the aggregate. So where the volume of the coarse aggregate per unit volume of the concrete mix is given to us in terms of different fineness modulus and the maximum size of aggregate. So in our case, the maximum size of aggregate is 19 mm and the fineness modulus of sand used is 2.6. So that tells us 6.64 meter cube of coarse aggregate by volume will be present in 1 meter cube of the concrete mix, right? So that is known. And then using this information and the dry rod and bulk density given to us, we estimate what is the coarse aggregate content, right, per meter cube of the mix. Right? So we multiply the volume by the density to obtain what is the mass present in 1 meter cube, right? So it was 1024 kilograms. And then to find out the fine aggregate content, we go for conserving the volume. So we sum up all the different volumes of the different components in the mix and then equate it to 1, right? So all volume in 1 meter cube of the mix and then equate it to 1, right? So the volume for the water content is 205 by 1000, for cement 456 by 3150, air content by volume 2%, for coarse aggregate 1024 by 2600, and finally for fine aggregate, the only unknown here is Fa by 2700, right? So using that conservation of volume, we find out that the fine aggregate content should be 638 kilograms in 1 meter cube of the mix, right? So with that, we find out the content of the different components per unit volume of the concrete mix, right? So that completes our design procedure. Okay, so that with that we will conclude week 6, right? Okay, we will continue our discussion and the problem solving sessions for the further week contents. Okay, so we'll meet again next week, same time. Okay, thank you for listening.